join me in welcoming to the Distinctive Voices podium, Dr. Greg Mosby.
Thank you, Greg.
Hello, thank you, Jennifer, for the introduction. As Jennifer mentioned, I'm Greg Mosby, and I'm here to talk to you about NASA Astrophysics Division's next big mission, our flagship mission, the Nancy Grace Roman Space Telescope Project. But first, I'll take a step back, because often when I walk into a room or we're out in public, I'm the first astronomer or astrophysicist that anyone has ever met. And I think people can have a hard time actually thinking about or pinning down exactly what is it that astronomers or astrophysicists do. And at NASA, to summarize it, our mission is to explore and expand our human knowledge with scientific discoveries. So as astronomers, what we do is use telescopes to make these scientific discoveries that can help expand our knowledge. And so I'll invite you to put on your astronomer or scientist hat with me and think about, well, why is it that these telescopes are so important? Why do we use telescopes? And we'll start by talking about one big question that we do ponder in astronomy, which is what the universe is made of. You and I can sense the universe around us. If I were to ask you all what the universe is made of, you could probably give me some good guesses. One of the first things you probably say is people. That's humans like you and me. You may then try to go to bigger scales. Here's the planets like Earth and all the planets in our solar system and even our dwarf planets in the solar system. The universe is made of planets. If you go even bigger scale, it's like, oh, we're in a solar system. At the center of our solar system is the sun. The sun is a star. The universe is also made of stars. And you go even larger. You say there are these large collections of stars that we call galaxies that are in a universe, like our Milky Way galaxy. So the universe is clearly made of galaxies. If you have taken some astronomy, you may even be able to go even finer detail and say that, you know, what you see in this picture of the Milky Way galaxy here on the right, those little dark regions are actually dust in the universe. So the universe has dust in it that can obscure visible light from us. And there's also gas in the universe. But when we actually use telescopes to observe the universe around us, we realize that the ordinary matter, that's the matter like you and me, is only a small fraction of the universe, only about 5%. So we can only really sense and observe about 5% of the universe, which is why we need telescopes. Telescopes help us observe and sense the universe beyond what we can do, just by our own eyes. Now, when we look at a galaxy, like the Milky Way galaxy, and we try to study the stars and the gas in those galaxies and what's holding them together, we find that there's missing matter. So this is an image of a plot that shows in the vertical direction the rotation speed of stars and gas in a galaxy. And in this horizontal direction, it's showing the distance from the center of the galaxy. In this dotted line on the bottom, we're showing the expected change of the rotation speed of these components as you move from the center of the galaxy. And this solid line that you see on top, that's much higher than this, is what we actually observe when we use our telescopes and instruments. And what we're seeing is that the stars and the gas in galaxies are actually moving much faster than what we would imply from the visible light that we see in these galaxies. This means that there must be some invisible matter that we can't see, it's not visible, that is keeping the rotation speed of these components in the galaxies higher than what we would expect. And you may be familiar with this. We call this invisible matter dark matter. And dark matter, we actually think makes up probably a quarter of the universe's content. And dark matter actually hosts the largest concentrations of normal matter. You see on this illustration on the left from Kaipak Stanford a simulation of galaxies, which are the yellow fuzzy blobs, and the dark matter that they're embedded in as this simulation is running. And you see that galaxies are kind of like beads on the thread of the dark matter in a universe. So they're enmeshed in it. So understanding dark matter in our universe is going to be a very important part of what we do in astronomy. Now, if we step beyond just looking at single galaxies, let's look at an ensemble of galaxies. When we study galaxies that are nearer to us and farther from us, the galaxies that are farther away from us seem to be moving away from us faster. This is an expected result because we do think the universe started in this Big Bang. So the universe is expanding. What's unexpected is when scientists looked at the galaxies that were much farther away, there seemed to be a change in this expansion, an acceleration in this expansion. So this led astronomers to scratch their heads again, that there must be some extra part of the universe that's causing this accelerated expansion. And we called it, quite uncreatively, dark energy. There's this something in the universe that's causing this recent expansion of the universe. Now, we study the expansion history of the universe by looking at the distances between galaxies. And you can kind of visualize this by looking at the plot I'm showing from a still of an animation on the left here. You have the expansion speed of the universe in this vertical direction. In the horizontal direction, we have time. And this little blue line is kind of a rendering of how we think the expansion speed of the universe has changed. And shaded in blue here, we see a recent acceleration of this expansion that would be being caused by dark energy. Now, dark energy seems to account for up to 70% of the universe's content. That's most of the universe. So surely understanding dark energy has to be something that we need to do in astronomy to understand the universe. Now, we were just at these really large scales. Even in our small corner neck of the woods inside of our galaxy, we still find surprises. We now know that our solar system is not alone. This is an illustration of 200 solar systems that were found in our galaxy by the Kepler mission. And now we know that there are thousands of these extrasolar planets. These are planets orbiting stars that are not our sun in our galaxy. And I'm showing here a snapshot that I took from one of our websites a couple of weeks ago that's showing all of these planets and how they were detected, color-coded. And in this figure, we're showing the planet's size, like how large it is, its mass, versus the orbital period of a planet, like how fast it orbits around its star. And you see that there are several different ways that we detect these planets in our galaxy. One particular method called microlensing, that we'll talk a little bit about later, actually has an estimate that it's likely that almost every star in the Milky Way has a planet around it. But still, we actually don't know precisely how many planets there are in our galaxy, what type they are, and probably the more tantalizing question, if any of those planets might actually harbor something that may look like life. So to understand the universe, we have to understand its parts. We have to understand dark matter, we have to understand dark energy, we have to understand exoplanets, and everything in between. And the Nancy Grace Roman Space Telescope is going to help us do just that. It's going to help us study how dark matter has changed and evolved in the universe, how dark energy has changed and evolved in the universe, and it's going to help us try to complete a census of exoplanets in our galaxy and almost anything in between. Now, the Nancy Grace Roman Space Telescope is going to be a 2.4 meter telescope. That's the diameter of the primary mirror that we're launching into space to study the universe in infrared wavelengths. So infrared wavelengths, these are the wavelengths that are much redder than what you and I can see. And we're using infrared wavelengths because that allows us to observe objects that are farther back in time, more distant in the universe. And it also allows us to see through dust in the universe. Dust obscures visible wavelengths of light in the universe. The Roman Space Telescope is going to be using two instruments. The primary instrument is the wide field instrument, and the technology demonstration instrument is the coronagraph instrument. It's actually using visible wavelengths. We'll talk about that shortly too. You can see on the left here a rendering of what the observatory looks like, and you can see where the wide field instrument is here, and where the coronagraph instrument is. You also see the deployable aperture cover here on the top. This is an important piece of the observatory because this deployable aperture cover is going to be covering and protecting our mirror when we launch into space, and when it's safe after launch to open up, we'll open it up, and then the universe will be open to this telescope. So Roman's wide field instrument is going to be taking the light from the telescope and focusing it down through a filter wheel where we're able to select what types of colors or wavelengths that we look at the universe through, and that will be imaged by 18 brand new sensors of the wide field instrument's focal plane. Each of these sensors has 16 million pixels, and that means like our wide field instrument as a camera would have almost 300 million pixels. So the illustration on the right gives you kind of a cartoon illustration on how light passes through the telescope, through kind of our intermediate optics, folded into the element wheel, which is how we select which wavelengths of light we look at the universe through, all the way down to our detectors that you see in kind of this smiley shape pattern. Now, the combination of our wide field instrument and our telescope is going to allow us to get images that are just as sharp as those images that you've seen from Hubble that are absolutely amazing, but over a much wider field of view. This is an illustration of how Roman's field of view compares to Hubble. You see this faint white square in this top corner is the field of view of Hubble. And this large overarching footprint is what Roman will see in one snapshot. Now, Roman actually has another connection with Hubble. So the telescope is called the Nancy Grace Roman Space Telescope, and it's named for Dr. Nancy Grace Roman, who was one of the first female executives at NASA and a chief astronomer, and she was instrumental in actually getting the Hubble Space Telescope approved through Congress so it could get launched into space. So it was kind of in honor of her contributions to astronomy that we decided to dedicate this important mission that's going to be uncovering mysteries in the universe in honor of her very important work in the field. And I think that's really appropriate since she was a very iconic figure in helping to make sure that NASA continued to do science in space. So how will Roman help us study these components of the universe? So Roman is going to be able to study dark matter in the universe with this wide field instrument. It's going to do this by measuring the positions and the shapes of galaxies. So by measuring the positions of galaxies, we're going to actually be able to see how dark matter clustering has changed over time. Remember, galaxies are embedded in the dark matter, so seeing how these galaxy positions have changed and how they clustering changed with time will allow us to see how dark matter clustering has changed with time. We'll also be able to actually measure tiny warping of galaxy shapes from dark matter. You see on this picture from the right, an illustration of what we call lensing. In this case, it's called strong lensing. What's happening is a foreground galaxy cluster that has a large amount of dark matter in it is actually causing the light from galaxies behind it to get bent and distorted and lensed into these beautiful arcs and other images of galaxies that you see here. Well, Roman is going to be sensitive enough to detect even smaller warping that we call weak lensing of galaxy shapes. So that's going to allow us to actually measure the distribution of dark matter between our spacecraft and the galaxies that we see their shapes warp in order to study the distribution of dark matter. And likewise, if we look at this distribution of dark matter over time, we can see how dark matter is clustering and how it's changing with time. Now, this is important because this may give us a clue to what type of particle dark matter may be. How fast it clusters It may depend on how heavy or light a particle dark matter actually is. Now, in a similar fashion, the wide field instrument is going to allow us to study the expansion history of the universe. So that's going to allow us to study dark energy. So Roman is going to do this by using these special stellar explosions that we call supernovae. So astronomers call supernovae standard candles. And we call them standard candles because you can think of them a little bit like a light bulb. If you buy a light bulb that's 100 watts, you know precisely how much energy it's throwing out into the universe. So if someone were to move that light bulb a really far distance away from you, you can measure the light that you observe and infer from how much you observed, from how much you know should be emitted, how far away that light bulb is. We can do the same thing with these really special explosions called supernovae. So Roman is going to observe hundreds of these supernovae to get really precise distances to galaxies. And by looking at how these distances between galaxies are changing with time, we're going to be able to map out that expansion speed history of the universe. Now, Roman is also able to measure positions of galaxies independent of these special stellar explosions. So by mapping those positions of millions of galaxies, we're also going to have like a cross-check of the supernovae results to really map out how dark energy might be changing in our universe. Now, Roman's wide field instrument will also help us study exoplanets. We're going to be using the Roman Space Telescope to study a central region of our galaxy that we call the bulge, monitoring around 200 million stars, looking for a characteristic magnification of a star we're monitoring caused by when a star passes in between our telescope and the stars we're monitoring. Now, you see on this illustration on the right, you get a lensing, a brightening of the star we're monitoring when a star passes in front of us. This is very similar to the lensing effect we just talked about. But if there's actually a planet on the star that's passing in between, you get some magnification from the planet as well. So you get another smaller, tiny blip, a micro lens that you see here from the planet. Now, this is a really sensitive technique of detecting exoplanets, and it'll allow us to detect exoplanets that are as close in as Venus and as far away as Neptune from their parent stars. So by looking at this central region of our galaxy, we're going to be able to collect the census of exoplanets in our galaxy. Now, Roman is also able to study exoplanets with a different method, instead of microlensing, using direct imaging. And this is with the coronagraph instrument. Now, the coronagraph instrument is a technology demonstration. It's actually going to be the first time that we use two technologies, deformable mirrors, and these really special optical masks in space. These are all being used to help light from a star that we're observing with the instrument to interfere with itself so that we can then see an orbiting planet around that star in visible wavelengths of light. On this illustration, this still here on the right, we're tracking how the light comes into the coronagraph instrument, hits the coronagraph instrument deformable mirrors, passes through these special optical masks that causes the starlight to interfere with itself, digging what we call a dark hole, and then revealing an exoplanet around this star on a visible wavelength sensor. Now, because the coronagraph instrument has these deformable mirrors, it'll be able to adjust and correct for any disturbances in the light coming into the instrument to strengthen the signal that we may see from a potential exoplanet. And this will be the first time we try this in space, and we hope that this will be a pathfinder to other missions that will go and try to do direct imaging of exoplanets in space. Now, I just gave you kind of a big, kind of small chunks of what Roman will do in these really big areas of astrophysics, dark matter, dark energy, exoplanets. Well, that's only really the tip of the iceberg. Roman is actually going to be able to study a vast amount of general astrophysics, and here in this slide is just some of the themes and the questions that we'll be able to answer with the data that we'll be getting back from the Roman Space Telescope. So we're really excited to get it in space. It's going to be a seminal instrument, and it's going to help us answer these fundamental questions And at NASA Goddard and with our partners, we've been really busy at work at making great progress in turning this picture of an observatory into the real thing. Now we've selected our 24 flight candidate sensors. These were the sensors that we collected to potentially place into the focal plane of the wide field instrument. The wide field instrument has 18 sensors, so we have 6 spares. In this picture here, we're actually showing one of our engineering units. So these are 18 engineering grade detectors, sensors on an engineering mosaic plate. And we build these engineering units to practice and rehearse operating, fitting, and designing our spacecraft in space. And on the right here, you may actually see somebody who looks familiar. That's actually me, holding one of Roman's sensors and also a cell phone camera for scale. So Roman's sensors have 16 million pixels. Like I said, they're 4K by 4K format. And each of those pixels is 10 microns in size. So when you put all that together, our sensors are much larger than the sensors that you'll find behind the cameras in your cell phones, because we have much larger pixels. Now, Roman has also finished coating all of the mirrors for the telescope. This is actually a picture of our primary mirror from our partners at L3 Harris. And we've also gone through and selected, out of those 24, the best 18 flight sensors to place into our focal plane. So this is a picture of the actual focal plane that's going to go into space. So we chose these 18 flight sensors after extensive testing at NASA Goddard with our detector characterization lab, and by looking at their performance as a whole focal plane system. Now, after we tested all those individual sensors, we placed them in the focal plane, we had to test them together with their electronics. We're gradually building up the system. On the left here, you see our technicians removing a cover from the focal plane. And after we got the focal plane situated and ready, we actually tested it at Goddard in a large vacuum chamber. So the way we test our instruments is we place them in these large chambers, we evacuate all the air out of the chamber to simulate space, and then we cool them down to really cold temperatures to simulate how we want to operate them in space. In the case of our detectors, we actually want to operate them at around 90 Kelvin. So that's around minus 300 degrees Fahrenheit. It's quite cold. But we get the best performance out of our sensors operating at these cold temperatures. While we're in the chamber in these tests, we also try to validate the performance of the sensors. So on the right here, I actually show a map of some of the data that we took during our tests at Goddard, where we shined some diffuse light on our focal plane array to check for the sensitivity of our sensors. And after all of our testing at NASA Goddard, we found that our sensors were performing beautifully well, and they met all of our requirements. So once the focal plane system was verified, validated, we shipped it to our partners at Ball Aerospace. Now they're called BAE Systems. Now, this video actually shows the installation of the focal plane system, the sensors and the focal plane electronics, into the wide field instrument. So what you see here, covered in that little bit of mylar on the top, is the cold sensing module where the focal plane system will live. You can also see, and you then see it in other photos, these kind of silver bands on the back of the focal plane system. Those are actually our cables that connect from the sensors to their electronics so that we can read out all 18 sensors at the same time. So we like to use a couple analogies when we talk about the focal plane system for Roman. One of them is quite literal. They're like the eyes of the observatories, because quite literally we're using the focal plane system to see, to actually guide and steer the telescope. They also are going to be what we look through to get all of our science data to uncover the mysteries of the universe. But another analogy that we use is that the focal plane system is like the heart of the mission. And I think that's a particularly apt analogy when you look at this really delicate operation. One of the things that comes to mind whenever I look at this this video, is like a surgery. There's all of these technicians, all these engineers working very meticulously, very carefully to install this very sensitive instrument that once it's inside of the cold sensing module, like the wide field instrument becomes complete. It becomes alive. We're able to finally test and operate it. So in this way, I think it's really apt to think about the focal plane system also as like the heart of the Roman Space Telescope. Now here on the left, you can see the wide field instrument all buttoned up together. You see this clear aperture here in the front is actually where light from the telescope will come in. Right outside of that aperture is actually a bicycle wheel-sized filter wheel. And it's like a carousel that has 11 slots in it. 8 for the imaging filters that we'll use, 1 dark element, and then a prism and a grism. Those are going to determine how we look at the universe, whether we get images or whether we get spectra of the universe. On the right here, you actually see the wide field instrument, which is right here, and this ground support equipment that we're pushing into a chamber at BAE Systems, their Titan chamber. And this is to test the wide field instrument just like we test the focal plane system. We evacuate all the air out of that chamber and we cool down the instrument to simulate how it will be in space. And we want to check and verify that everything is working as expected and that we get the expected performance. So here in the snapshot on the right, I'm showing some of our test data where we're looking at what we call the noise, or what you can think of as like the precision of our sensors. And we found that throughout our test at BAE Systems, our sensors, even inside the wide field instrument, continued to perform just as we expected and to meet all of our mission requirements. At BAE Systems, we even took the whole wide field instrument and underwent vibration testing and acoustic testing, and then retested the whole system cold again to verify that we can still maintain performance of the instrument. And after the instrument's performance was validated and checked out, we sent the instrument back to Goddard. So here's an image of the wide field instrument being unpacked at Goddard. I think our comms team may have even done a video of them kind of unboxing it that you can find on our social media. What you'll see here at the top is the wide field instrument radiator. And there are actually covers on this radiator to protect this really sensitive surface. This radiator is actually how the wide field instrument will actually cool itself in space. We're a passively cooled mission. And you'll notice that everything seems to be covered in this gray plastic. Well, this is actually not plastic, it's what we call thermal blanketing. And this thermal blanketing is what we use to essentially carefully control the thermal properties of the instrument to be able to keep it as cold as we like and to keep it from not getting warm and not letting any stray light inside of the instrument. Now, as soon as we got the wide field instrument at Goddard, we started integrating up the instrument with all the other components that were at Goddard. The coronagraph instrument was already at Goddard. And soon after the wide field instrument arrived, we got our telescope. So we could start integrating the wide field instrument, the telescope, and the coronagraph instrument. This is actually a photo of the lift to lift up the telescope, the coronagraph instrument, and the wide field instrument onto our spacecraft bus. So you see here at the top is our telescope. You can see the coronagraph instrument right here, and you just see the bottom of the wide field instrument radiators here toward the back. On the bottom here, you see the spacecraft bus. Now, the spacecraft bus houses the power, it houses the brains, that's the computer, and it houses the thrusters of the observatory. And so once we put all these components together, we call them the spacecraft integrated payload assembly. It's really long to say, so we abbreviate that and we call it the SCIPA. And the SCIPA is at the current integration level that we're at right now for the project. Now, the SCIPA testing is going to be beginning this summer. So we're rapidly at work right now trying to make sure we get all of the pieces together in line. On the left here, you actually see a view inside the chamber at Goddard that we're going to be testing the SCIPA inside of. We do these Pathfinder tests so that, like we say, we can rehearse and find any issues, correct any problems, and learn from these rehearsals what to do with the real thing. And on the right, you see the fully integrated SCIPA that's going to be going into that chamber. So the testing will be beginning this summer. It's going to be the first time that we actually see how our telescope performs with the focal plane sensors. It's going to be the first time we operate all of our instruments with the spacecraft. So it's going to be one of our last tests before we actually button up the entire observatory and send it to Cape Canaveral to launch. So we're really anxious about the upcoming summer and meeting this milestone on the project. Now, it's well on its way. Like, we're launching no later than 2027, and we're well on our way to creating, the real thing from these images. You didn't get to see pictures of the solar panels or some of these outer barrel assemblies or the deployable aperture, but all of those components are also already at Goddard and also have been tested. And we're really looking forward on the science side of seeing what Roman will teach us about dark matter, about dark energy, and about exoplanets and everything in between. And I hope you'll follow us on Twitter and our social media to keep up to date with the project. We just released some brand new content showing all of the hardware and integrations that have been happening over the past year. And I hope you all are as eager as I am to see what Roman will reveal to us about the universe. And I'll stop here for questions. Thank you.